In this talk, when you see the expectation of a function applying on x, look at it simply as an integral of the function versus this image measure. The image measure, this measure is called the distribution of x. Now, I will start the talk which focuses on the concept of complete monotony, on Laplace transforms, on Milling transforms, and what we can do with this object. And the finality of this talk is to solve an odd problem due to two American authors, HARKNESS and SHANTARAM, who raised the problem in 1969, and I will try to convince you that this problem is now solved. Then, this talk is divided, let's say, into three parts. The first part is my joint contribution to the topic of complete monotonicity, and it's a joint work with Rafiq Agash, which is present with us today. The second part will be more probabilistic and solves the problem of HARKNESS and SHANTARAM, and the solution will be explicitly given in part 3. Then we could say that part 1 could be dissociated from the other, but there is an intricacy. Part 2 and 3 was done jointly with my doctoral student Nouf El-Harthi and Fathi Bouzafour, who helped me with his knowledge in analysis. We start with, of course, we need some notations and some settings. We introduce the delta difference operator, which is an increment, and his companion, theta. Of course, you will see a constant C appearing. C will vary. The delta and theta difference operator could be also iterated, and we get this very easy formula. The iterate of the delta C operator is given by this sum and difference. And the same holds for theta. We need a lot these operators. Why? From now on, we focus on the class of what we call completely monotone function. When you see, do you have a pointer, sorry? No. No? Okay. When you see f for the circle will be or a function or a sequence. The domain D, in order to fix the ideas, will be or 0 infinity or the set of integer. We say that f is completely monotone. This is the basic definition. If you apply the difference operator n times and you multiply it by -1 power n, you recover a positive function. That means the first increment is negative, apply a second increment, it will be positive, and so on. We say that f, seen as a function or a sequence, is completely alternating if you have the opposite sign. The first increment will be, the first difference will be positive, the second negative, etc. What are these kind of functions or sequence? What are they? What is their structure? Just focus on this condition. It's very surprising to discover. This has been discovered by Bernstein, the guy of the polynomials, that necessarily f, if f is a function, necessarily f is infinitely differentiable. It's not obvious to see it with only this kind of condition. not only f is infinitely differentiable, but it also has a representation as a Laplace transform of a measure. Then any function satisfying this difference condition is necessarily infinitely differentiable, and the continuous, the analogous of the discrete differentiation is that f is n times differentiable, and the successive derivatives alternates in sign. And this is equivalent also to say that f is the Laplace transform of some measure. This is an old theorem due to Bernstein in the early last century. What are the completely alternating function? I restricted myself to completely alternate function which are positive. Why? Because at the contrary to the completely monotonic function, we don't require for completely alternating function to be positive. They could be also positive or negative. But the increments start to be positive when you apply the first increment. Then, a completely alternating function, a positive completely alternating function, coincides with what we call the class of Bernstein functions, which are the class of positive functions which have a first derivative which is completely monotonic. Then Bernstein function could be seen as the positive antiderivatives of the completely monotone functions. When you look at the result by this way, you could say that, okay, the guy is presenting some integral representation, and that's it. What the question, the next question would be, why these kind of objects are so important? I will try to convince you here with 2 lines the importance of this kind of representation. If you allow me, I will switch over the light and write just 2 lines. This stuff intervene. For example, you have a measure nu, and you look at this Laplace transform. Of course, everybody knows that everybody knows the Fourier theory, Fourier transform theory, Laplace transform theory. If you take a square, it's simply the Laplace transform. This is the Laplace transform of nu in lambda. If you multiply f by itself or by any function, it's simply the Laplace transform of nu convoluted with nu. Now, what happens if instead of considering then in general, this is the n convolution. Okay? What happens if you replace the integral n by any positive real number? Does it remain? Is it the Laplace transform of something? The answer, of course, is in tautogénéity is no. The Laplace transform elevated at the power 1/2 doesn't give Laplace transform. It's the same story for Fourier transforms. Then, how to characterize the set of measure nu such that the Laplace transform elevated to some power t remains completely monotone. This is another story, and the problem is old and solved, and the theory is well settled. We know everything. In order that this condition holds for any t, it's a necessary and sufficient condition is that the Laplace transform of nu is said to be infinitely divisible. Infinitely divisible, why? Because if you get this condition, this is equal to say that for any integer n, there exists a sequence un such that nu could be deconvoluted into distributed with itself n times. Then it's the concept of deconvolution. It's not the concept, it's the opposite operation of deconvolution applied on U. Not all the measures are infinitely divisible in the sense of convolution. And the total characterization is that the Laplace transform of U, if you take the logarithmic derivative, this function should be completely monotone. Minus log Laplace differentiated, if you get a completely monotone function, then nu is infinitely, if and only if, actually. If and only if minus log Laplace of nu could be written as a Bernstein function like this. Okay? Then this class of functions are not simple integral representation. They handle a nice theory. They are present in the nice theory of infinitely divisible measures. A simple example of infinitely divisible measure is the Lebesgue measure restricted on R plus. I just forget to say that whenever you get an infinitely divisible measure, then you can get a convolution symmetry of measures such that nu1 is the initial infinitely divisible measure, and this convolution symmetry obeys to this evident equation. And as an example, take the Lebesgue measure restricted on R plus. The x denotes the Lebesgue measure restricted on R plus. And this family of measures obeys to this convolution symmetry. This is a trivial example. X to the power t minus 1 divided by gamma of t. Then, this class of function is extremely important. Of course, you can have Fourier versions of all what I'm saying. In order to be more clear, I restricted this talk on measures supported by R plus, in order to handle Laplace transforms, etc. Then, what are the completely monotonic sequences? This is an old theorem due to Hausdorff. A sequence is completely monotone if and only if it corresponds to what we call a moment sequence. Each term of the sequence AK is represented as a moment. There is a unique measure nu generating the whole sequence. Okay? And completely alternating functions have also a form familiar, which is closely related to the form of the Bernstein functions. Then we have the continuous version and the discrete version for complete monotonicity and complete alternance properties. We say that the sequence AK is minimal if it's completely monotone, and if you delay it, if a simple delay on the first time, make it not completely monotone. And the same definition, we will take the same definition for complete alternate sequences. And Wieder in 46, and later with some other means, it's not that obvious that the sequence is minimal if and only if the representing measure here gives no mass to 0. Now, we get into the subject. We know what is evident is that when you take, look at this, when you take a completely monotone function, lambda is a real number, a positive real number. Take it in k, f of k becomes exponential minus kx nu, and make a simple change of variable. You recover that f of k has a structure. The change of variable is evident. U is exponential minus x. F of k becomes a moment sequence. Then, from any completely monotone function, you can build the sequence ak equals fk, which is completely monotone. Okay, you need some technicity, and it's not that direct. Huh? This is the Hausdorff characterization of completely monotone sequence. Any completely monotone sequence could be interpolated by a completely monotone function. Okay? Then the natural question is, if you start from a function and you know that the sequence ak equals f of k is completely monotone, could you say that f as a function on R plus is completely monotone? You understand the point, I hope? No? You start with a function, which is nothing, and you build the sequence ak equals f of k. You know that f of k is a completely monotone function. Could you say that f is necessarily completely monotone as a function? Okay? The answer is not evident. Because another way of asking the question, you start with the completely monotone sequence. You know that it's interpolated by a function, but by a completely monotone function. But is this function unique? You know the problems of interpolation that we use to teach at the low-level schools. You start with endpoints and you interpolate them by a polynomial. Okay. And you do some stuff related to numerical analysis, and we start there. Here we are interpolating the function, the sequence, and we want to have unique interpolation because we want to interpolating the whole sequence. Okay, and the answer to this problem will be a kind of converse to Hausdorff moment characterization problem. There are a lot of moment problems, like the Hausdorff one, the Hamburger one, and so on. Hamburger deals with the representing measure on R. Okay, this is our answer. The function psi is completely monotone if and only if the sequence C of k is completely monotone and minimal. And psi admits a holomorphic extension on the right half complex plane. Open right half complex plane. The motivation, my motivation on this problem started when I reviewed a paper submitted by these three German authors, May, Schenk, and Scherer, to Journal of Theoretical Probability, where their main result was the following. A function psi is completely monotone if and only if it's continuous, and, look at this condition, psi of fixed k is completely monotone for any x in a dense subspace of R+. Then you see here a parameter intervening, and this condition should be true for any x. And I told myself this is perhaps too much requiring. Actually, you are filling R, this R plus by this means. What happens if X is fixed? Huh? Then my answer is the following. I don't have any parameterization here, and the first condition is extremely natural. How can we solve? How can we prove this kind of results? Of course, we can get some lighter version as corollaries. There is a slight difference here. Here, the psi function is defined on R plus, 0 included. Not all completely monotone functions are defined at 0. For example, the function psi of lambda equals 1 over lambda for lambda strictly positive. This is a completely monotone function. But this function is not defined at 0. And we can have troubles. The troubles are raised by considering this corollary. Just make a small delay with any sequence going to 0. Okay? And the characterization of completely monotone function goes through the sequences. As an easy corollary, if two functions coincide on integer from a certain rank, then necessarily they are equal. If two functions, completely monotone functions. Of course, everybody knows that the Fourier transform is injective on a proper subspace. The Laplace transform is also injective. Okay, but here we consider only the restriction of completely monotone functions along a part of the integral. Huh? What kind of tools did we use? We can approach this problem by two ways. First of all, we needed to make bounded, which was to make some functions bounded when at the origin they are not bounded. Then we needed to apply the delta differences in order to make things bounded. Then the answer for completely Bertrand functions, the trivial Bertrand function is f of lambda equal lambda. Then a function phi is a Bertrand function if and only if its restriction on the integral forms a completely alternating function, and it admits an allometric extension on the half real plane with some bounded condition on the increments. And we can also extract an equivalent corollary to the equivalent to the situation of completely monotone functions, and two Bertrand functions, if they coincide on a small part of n, then they are necessarily equal. We used these tools based on the delta difference. First of all, notice that you have preservation of complete monotony property under the delta and delta operator and theta operator for Bertrand functions. Here, the theta operators make any Bertrand function bounded. It remains a Bertrand function. And this is crucial if a shift, the difference operator applied to a completely monotone function is completely monotone, then necessarily psi is completely monotone. And the same holds by replacing the psi by phi, which is a Bertrand function, and replacing delta by the theta operator. We also needed to extend some results in the literature. We appeal to the Chronometer Theorem, which is not very known by analysts. You know, everybody knows that taking a limit for a function, taking a limit along the integer or along the real number, it makes a big difference. The concept of limit is well settled for when you take x real going to some limit, but if you take limits along the integer, think about the sawtooth functions. You can have limits along the integers, but not a proper limit when x goes to plus infinity. Then Chronometer proved that if you take the limit when x, look at this as an x, limit of lambda plus x minus h of x goes to something, then necessarily this something is linear. Okay? We proved this result, but by taking, if two functions h and l are linked by this kind of limit, then also necessarily the limit L is linear, and the limit will hold also along the real numbers, and it will hold also uniformly on each compact set of R+. We also appealed to a very well-known theorem to specialists in complex analysis. Professor Lorini could confirm this fact. The original version of Blasch's theorem is set on unit disk, but there is no intricacy to transform it on C+. Two holomorphic functions defined on the half-open set are identical if and only if they coincide along a sequence of a complex number on C+, such that this condition, summability condition holds. Okay, this is the first approach. We also provide the second approach, which is purely analytical and avoids the complex analysis stuff. When you have a difference equation, everything comes from the delta and theta operators, and after apply the log, etc. When you have a difference equation like this, that means that if you start from a function j, which is log concave, and which satisfies easy obtainable conditions, j should be slowly varying at infinity. If it's differentiable, an will be the logarithmic derivative taken in n, and you see here a familiar Euler constant built with j. You start with j, you build your equation, and if j is log concave, you will recover unique log convex function, which is explicitly given by this formula. Of course, when j is the identity, the unique solution is the gamma function. This is a generalization of the difference equation built for the gamma function. And we had to combine this tool with also a known concept. No, not so known. I checked it. This concept is not even known for specialists in numerical analysis. I had some conversation with colleagues in numerical analysis. The people from numerical analysis, most of the time they consider only the interpolation at finite stage. That means you have endpoints and you interpolate by polynomials and you approximate, etc. Of course, you can always approximate a smooth function by a sequence of polynomials, but most of the time you say nothing about the rest. The difference between f and Pn, which is the approximating polynomial. Here, what is written here? How can we be sure that the sequence of polynomial, the rest, the difference, goes to 0. That means f is expandable into this form. Of course, we have the known conditions with the series expansions or analytic functions, but here the conductive term is not the usual 1z to the power k, but it's the descending factorial of z. And what you cover here, under these conditions of at maximum polynomial exponential growth, is that f is expandable into this form, and necessarily what replaces the kth derivative at 0 is the delta difference at 1 iterated k times divided like this. Then these tools plus some additional tools allowed us to solve this natural equation. And now we finished with the purely analytical part, and we will go to the more probabilistic oriented part of this work. The last part, as I told you, was motivated by a paper, and we worked on this topic with Rafiq Agash. The second part will be a little bit connected, not actually, and it was it's a paper. Okay, this work was submitted to Pacific Journal of Mathematics, and we'll still be waiting for a long time for the reports. This part solves a very old problem due to HARKNESS and SHANTARAM, and raised in 1969. I will try to convince you about the importance of the problem by the probabilistic point of view and also analytic point of view. So first of all, we consider positive random variables and what we call their Milling transform. What is Milling transform? It's simply the integral of x power lambda versus the distribution, the measure of x. Don't be afraid about the notations of expectation. It's an integral. Of course, most of you know the concept of Milling transform, if you are analyst at least. You have some elementary property. Actually, the idea of this paper started when I was supervising the thesis of my student, and times to times naive questions could raise very interesting problem. This is why I was co-writing with my student, because the original idea came from one of her apparently naive questions. And we looked at a little bit at the literature, and little by little we discovered this open question by chance. And I decided to handle it. It took a little bit of time. The question was purely analytic. And my approach is probabilist. Then, what are the elementary properties of the Milling transform? It's a log convex function such that this kind of ratio as a function of t is always non-decreasing. And we need some formalism, and we need to improve also some results. Widder, 1940, proved that if the Milling transform of two distributions coincide on some bands, complex bands, alpha with the extremities alpha and beta, you understand? Then necessarily the two distributions are equal. We start by improving this result. It's enough to check that the two Milling transform coincide on a small interval. You don't need to go to complex bands. Second, I need to introduce what is the concept of biasing the distribution. You start with a distribution which is a measure with mass 1 supported by R plus. You put some perturbation, power weight, and you normalize it in order to keep the structure of a probability measure. Then you are building a realization of X, which is called X index T, which has this distribution. The size basing is closely related to the Milling transform, because the Milling transform of the size basing is simply this ratio of Milling transforms. Look at this as a function of lambda, and T is fixed. And any integral could be, this is elementary, to be honest. And what is the effect of size basing? 2 times, you just add the parameters. The effect of the power is here. For people who doesn't understand a lot the concept of independence of between random variables, 2 random variables x and y are independent if the probability distribution of the couple is the tensorial product of the 2 distributions. Okay, what are we going to do with this concept of Milling transform? We did some preparation. For people who already taught probability theory, you know, at the bachelor level, 3rd level bachelor level, in most of the university, when you teach probability as a lecture of analysis, at the end we always deal with the limit theorems. Limit theorems for random variables could be or in the distributional approach or also in the almost sure approach. When we deal with the limit theorems in the distributional approach, we have a lot of criteria ensuring that the distribution of xn goes to the 1 of x. What does it mean? In the analytical point of view, that means that the measures converge tightly, or also equivalently vaguely. It's the vague or tight convergence of measures. The concept of distribution, convergence in distribution for random variables is exactly the concept of convergence of measure in the tight or vague sense. They are equivalent when the probability measure have a uniformly bounded mass, the sequence of measures. You know, we are in probability, everything goes smoothly. Then we needed first to enlarge the classical definition. The usual concept of tightness and uniform integrability are given classically by Belinsky. We enlarge them. We require a little bit less restrictive definition in order to write things. And we provide this kind of limit theorems. Xt goes to x infinity in distribution if and only if, plus some uniform integrability condition, if and only if the Milling transform converge. This is known. The sequence of Fourier transform converge, then the measure converge in the vague sense or tight sense here. Here we handle the Milling transform. Then we already settled the theory. There is another concept. When look at W, T, UT, VT, it's a product. Here it's an independent product. These are random variables. Of course, it's very elementary if everything is deterministic. If you know that this guy converge and this one converge for limit which are not 0, not infinity, then necessarily this one converge. When you handle random variables, it's not the simplification, you know, limit over limit doesn't make sense. Okay? You understand the difference between random variables and real sequences. W2 converge, VT converge, then necessarily UT converge, but in the sense of distribution. Huh? Okay, then we needed also this criteria. And now I get into the subject. But before, perhaps I will skip this part, which is purely probabilistic. This is the concept of beta and gamma distribution. We also need the concept of T-monotone function. What is a T-monotone function? Look at T as an integer, a function. F is n-monotone. What does it mean, n-monotone? It's like the first concept. The derivatives alternate until the stage n. Okay? In the first part of the talk, stage n was infinity. Then a function is convex if it's two monotone. Okay? It's decreasing if it's one monotone. But here I consider T as a real number, positive real number. A density function associated to some random variable is T monotone if and only if it's a mixture between what we call a beta variable, which is a random variable between 0 and 1, and whose density is explicitly given by, the integrand in the beta function. If and only if this guy has a T-monotone function, if and only if it's a mixture with a beta distribution with some random variable which is based biased at the order T. And this simple remark could be also provide an alternative proof for Bertrand characterization theorem for completely monotone functions. Because the function is T monotone for any T, simply completely monotone function. Completely monotone function. Do I still have enough time? No?
Maybe 5 minutes.
5 minutes, okay. I took too much time probably. What is the problem of HARKNESS and SHANTARAM? They start with the random variable. That means they start with the probability measure, and they apply what is classically called the stationary excess operator. You integrate, normalize, and you get a new random variable. That means you get a new distribution by this means. Then, if you look at the nth iterate of this operator, you call it En applied of x. This is a realization of the distribution obtained by iterating n times this operator. Notice that we can have also continuous time version. If you define Et of x by this independent product, whose effect on the distribution is a kind of Millen convolution, I mean, it's a multiplicative convolution. When t is an integer, it corresponds exactly to E1 iterated n times. And HARKNESS and SHANTARAM solved this problem. If you start with x, you apply this operator n times, you get a new distribution, or for probability you get a new random variable. What kind of normalization could you put in order to make this converge? They obtained sufficient condition, and they proved that one of the candidates of the limit here could be what we call the log normal distribution. This kind of theorem is very familiar for probabilists and also analysts. Everybody who taught the probability, third level probability lecture at the bachelor always teach that if you start with x1, xn ideal random variables, and you build the partial sum Sn, and you require that you have a mean and you have a variance, then the center limit theorem, what do you need for Sn? What kind of normalization you need for Sn? You need square root of n in order to make it converge in distribution. To what? To the famous Gaussian, standard Gaussian distribution. This is very classical. Then what we present here has the vocation of this kind of theorem. We don't take partial sums. We make successive operations on the initial distribution, and we look for a normalization in order to make it converge in distribution. Then, how can we solve? I told you that the big point is what kind of limit could we obtain. Until recently, a lot of people, and we will see the reference, worked on this topic, and each time gave some criteria, but at the end they only give as trivial example the first candidate proposed by HARKNESS and SHANTARAM, which is the log normal distribution. What we prove here, that actually the log normal distribution is the unique distribution. There is no other limit. How did we handle this problem? HARKNESS and SHANTARAM considered only the discrete version. We had the idea to swap to the continuous version. T is not an integer, but T could be positive number. And we just noticed that the stationary excess operator in the continuous time actually operates like, has this form, with here a beta mixing. And then it's enough to focus on what we get here and to look for the proper normalization needed for the exporting. And the stationary excess operator in the continuous version actually has exactly this form. We simplified it. And we showed that necessarily the limit will be a mixture between an exponential distribution with a log normal distribution. I will perhaps accelerate a little bit and conclude. This is the conclusion. The conclusion is that I prepared this thanks, but actually I guess that only the third line will apply here today. And thanks to Dr. Umber's second line.